You know, most people think time travel is some kind of science fiction nonsense, something you see in the movies with flashing lights and spinning machines. But I'm going to tell you something that's going to sound absolutely crazy. Every single time you use the GPS in your phone to find the nearest coffee shop or navigate to some address, you are directly experiencing the effects of time travel, not metaphorically, not approximately, actually experiencing it. And if we didn't account for time travel and those satellites orbiting above your head, your GPS would be off by miles within just a few minutes. Completely useless. Now, when I say time travel, I don't mean jumping into the future or going back to visit dinosaurs. I mean something much more subtle and much more real. Time itself is running at different rates depending on where you are and how fast you're moving. The clocks on those GPS satellites are literally ticking at a different rate than the clock on your wrist. And this isn't some tiny, ignorable effect. This is a huge problem that engineers have to solve every single day, or the whole system falls apart. Let me start by telling you what GPS actually does, because most people have no idea. They just tap a screen and boom, there's a map with a little blue dot. Magic. But it's not magic, it's timing. The whole thing is about timing. You've got about 30 satellites up there, about 12,000 miles above the Earth, zooming around the planet twice a day. Each one of those satellites has an atomic clock inside it, one of the most precise timekeeping devices humans have ever built. These clocks are so accurate that they lose less than 1 second every 100 million years. Incredible machines. Now here's how it works. Each satellite is constantly broadcasting a signal. That signal says, hey, I'm satellite number 7, and the time right now, according to my atomic clock, is exactly this. The signal travels at the speed of light, which we know very precisely, about 300 million meters per second, and your phone receives that signal. But here's the key. The signal took some time to get from the satellite to your phone. So your phone looks at the timestamp in the signal, compares it to its own clock, and figures out how long the signal was traveling. Since we know the speed of light, we can calculate the distance. If the signal took, say, 70 milliseconds to arrive, we multiply that by the speed of light and boom, we know we're about 21,000 kilometers from that satellite. But here's the thing. One satellite doesn't tell you where you are. It just tells you you're somewhere on a sphere centered on that satellite with a radius of 21,000 kilometers. That's not very helpful. So you need more satellites. With 2 satellites, you narrow it down to a circle where those 2 spheres intersect. With 3 satellites, you get it down to 2 points, and one of those points is usually way out in space or underground, so you throw it out. With 4 satellites, you've got your exact position in 3 dimensions, plus you can sync your phone's clock perfectly with the satellites. So the whole system depends on incredibly precise timing. If the clocks are off by even 1 microsecond, 1 millionth of a second, your position is wrong by 300 meters. That's the length of 3 football fields. If the clocks are off by a millisecond, you're off by 300 kilometers. The whole system is garbage. So you absolutely must have those clocks synchronized to an absurd degree of precision. And here's where Einstein walks in the door. Because Einstein told us back in 1905 and then again in 1915 that time is not this absolute thing ticking away the same for everybody everywhere in the universe. Time is relative. It depends on how fast you're moving and how deep you are in a gravitational field. And both of these effects matter for GPS satellites. Let's start with the speed thing, which Einstein figured out in his special theory of relativity. This is the one everybody's heard about. If you're moving really fast, time slows down for you compared to somebody who's standing still. Now the GPS satellites are moving fast, about 14,000 kilometers per hour, which sounds like a lot. But compared to the speed of light, which is over 1 billion kilometers per hour, it's actually pretty slow. Still, it's fast enough that time dilation kicks in. There's a formula for this, and I'm not going to write it down because we're just talking, but the idea is simple. The faster you move, the slower your clock ticks compared to a stationary clock. For the satellites, because they're moving at 14,000 kilometers per hour, their clocks run slower than clocks on the ground by about 7 microseconds per day. 7 millionths of a second per day. That doesn't sound like much, but remember, 1 microsecond of error means 300 meters of position error. So after 1 day, if we didn't correct for this, your GPS would be off by about 2 kilometers, just from the speed effect alone. Now here's the really beautiful part. Einstein didn't stop with special relativity. He went further and developed general relativity, which tells us that gravity also affects time. The stronger the gravitational field you're in, the slower your clock ticks. This is harder to understand intuitively, but let me try to give you a picture of it. Imagine spacetime, this four-dimensional fabric that we're all embedded in, like ants crawling on a rubber sheet. Mass, like the Earth, creates a dent in that sheet. The closer you are to the Earth, the deeper you are in that dent, the stronger the gravitational field. And Einstein's equations tell us that time runs slower the deeper you are in that gravitational well. So a clock on the surface of the Earth, down here in the thick of Earth's gravity, ticks slower than a clock way up in space where gravity is weaker. Now the satellites are 12,000 miles up. At that altitude, Earth's gravity is weaker than it is down here on the surface. So the clocks on the satellites, because they're in a weaker gravitational field, actually tick faster than clocks on the ground. How much faster? About 45 microseconds per day, 45 millionths of a second per day faster. So now we've got two effects pulling in opposite directions. The satellites are moving fast, so special relativity says their clocks should run slower by 7 microseconds per day, but they're also higher up in a weaker gravitational field, so general relativity says their clocks should run faster by 45 microseconds per day. What happens when you add them together? The gravitational effect wins. The net result is that the satellite clocks run about 38 microseconds per day faster than clocks on Earth. 38 microseconds per day. If we didn't correct for this, your GPS position would drift by about 10 kilometers per day. After a week, you'd be off by 70 kilometers. After a month, you'd be off by hundreds of kilometers. The system would be completely worthless. So what do the engineers do? They can't just ignore this. They have to account for it. And here's the absolutely crazy part. Before they even launch the satellites, they program the atomic clocks to tick at a slightly slower rate than they would on Earth. They intentionally detune the clocks. On the ground, an atomic clock ticks at a frequency of 10.23 megahertz, but the clocks on the satellites are set to tick at 10.22999999545 megahertz, just a tiny bit slower. So when the satellite gets up into orbit, experiencing weaker gravity and high speed, the clock speeds up by exactly the right amount to match the rate of clocks on the ground. Let me say that again because it's so important. We have to build time travel into the clocks before we launch them. We have to account for the fact that time is going to run differently up there than it does down here. If we didn't do that, the whole GPS system would fail immediately. And this isn't some theoretical correction that we think might be happening. We've measured it, we've tested it. In the early days of GPS, they did experiments where they turned off the relativity corrections just to see what would happen. And sure enough, the system started drifting immediately, accumulating errors at exactly the rate that Einstein's equations predicted. So we know beyond any shadow of a doubt that time is running at different rates in different places. Now let me tell you why this is so philosophically profound. For thousands of years, humans thought time was this absolute universal thing. Newton thought so. Everybody thought so. The idea was that there's some cosmic clock ticking away, and everyone everywhere in the universe experiences the same flow of time. If it's 3 o'clock here, it's 3 o'clock everywhere. 1 second here is 1 second everywhere. But Einstein showed that's completely wrong. Time is not absolute. It's relative. It depends on your motion and your position in a gravitational field. Two people can experience time at completely different rates, and both of them are correct. There's no preferred reference frame. There's no universal now. And this has the most bizarre consequences. Imagine you have a twin, and your twin gets on a spaceship and flies away at 99% the speed of light, zooms around for what feels to them like 1 year, then comes back. When they land, you've aged 50 years and they've only aged 1 year. This is the twin paradox, except it's not a paradox at all. It's just how time works. And we see this effect in miniature with GPS satellites every single day. Now, I want to be clear about something. This is not time travel in the sense of going backwards in time. Einstein's equations don't allow that, at least not in any practical way. What we're talking about is differential aging, different clocks ticking at different rates. You're always moving forward in time, but the rate at which you move forward depends on your circumstances. And here's another beautiful thing. The GPS system is essentially a laboratory for testing Einstein's theories. Every day, billions of people around the world are unknowingly participating in a giant relativity experiment. The fact that GPS works, the fact that it's accurate to within a few meters, is direct experimental confirmation that Einstein was right. If special relativity were wrong, if general relativity were wrong, GPS would not work. It's that simple. Think about how amazing that is. Some guy sitting in a patent office in Switzerland in 1905, scribbling equations on paper, with no computers, no satellites, no fancy equipment, figured out that time is relative. And now, over 100 years later, we depend on his equations every single day just to find the nearest pizza place. And it's not just GPS. Time dilation affects all kinds of things. Particle accelerators have to account for it. When we accelerate particles to near the speed of light, they live much longer than they would if they were sitting still because time slows down for them. We see muons, these unstable particles created in the upper atmosphere by cosmic rays, reaching the ground even though they should decay long before they get here. But because they're moving so fast, time slows down for them. And from their perspective, the atmosphere is much thinner because of length contraction, another relativistic effect. So they make it to the ground. Every single experiment we've ever done confirms Einstein's predictions. And yet, it still feels wrong, doesn't it? It feels like time should be the same everywhere. Our intuition, built up from living at human speeds in weak gravitational fields, tells us that a second is a second is a second. But our intuition is wrong. Nature doesn't care about our intuition. And I think that's one of the most important lessons physics teaches us. The universe is under no obligation to make sense to you. It doesn't care if you find something counterintuitive or weird or hard to believe. The universe just is. And our job as scientists, as curious human beings, is to set aside our preconceptions and actually look at what nature is telling us. When you do the experiments, when you measure carefully, when you test the predictions, you find out that time really is relative. Clocks really do tick at different rates. And this isn't some abstract mathematical game. It's real. It's measurable. It's in your pocket right now. So the next time you pull out your phone and ask it for directions, take a moment to appreciate what's actually happening. You're receiving signals from satellites traveling at 14,000 kilometers per hour, 12,000 miles above your head. Those satellites have clocks that are ticking faster than the clock on your phone because they're in a weaker gravitational field. Engineers have accounted for both special and general relativity to make sure those clocks stay synchronized, and because of that, you can find your way to wherever you're going with incredible precision. You are directly experiencing the effects of time travel. Time is passing at a different rate up there than it is down here. And the only reason your GPS works is because brilliant engineers understood Einstein's equations and built that understanding into the system. That's not science fiction. That's science fact. And to me, that's a lot more amazing than any Hollywood movie about time machines, because this is real. This is the actual universe we live in, strange and beautiful, and utterly indifferent to what we think should be true. And honestly, I find that thrilling. The universe is weirder than we ever imagined, and we get to figure it out piece by piece, experiment by experiment. What could possibly be more exciting than that?